everyone, how are we doing? We've got Blake here, we've got Shelby here, we've got Evan here. Everyone's having some fun, some chapter 14. Who knows where to go for the review? I had a few people emailing me, asking me about the review. Review 2 is where to go. We're going to start here, it looks like, with the grocery store question. I think I saw another one. Standardized test scores. Have a mean and unimodal. Well, thank you so much, Evan. I appreciate that. We got to wake up Mewbot. Sleeping on the job right here. Review Brian. You're cracking me up. Let's see right here. Okay. Where the pop-out chat's over there. Let's get my Pearson up and going. My Pearson. We're gonna have my Pearson up and going. We can do that. I think we haven't done the grocery store one yet. The grocery store one's like the waiter waitress problem. So it's a really good one. It's a really good practice one. What does chapter 13/14, what is the number one thing you have to do for those chapters? Chapters 13/14, you need to know what? What do you need to know for chapter 13/14? The number one thing. What is the number one thing?
Notation, brother.
Notation. It's all about notation. You have to know the notation. You have to know how the formulas work. So make sure to know the notation. Why does that do that? Getting the thing loaded up. Sometimes it doesn't show me the replace questions button. I don't understand. My Pearson's weird. My Pearson's weird. Okay, can I now see the replace buttons question? Replace. Is it because this? I swear it wasn't there. I swear it wasn't. Now reload the page and it's there. Okay, so we almost got the question up and going. Get ready to do the notation. We're going to find that grocery store question company. I think it's right here. A grocery store receipts show the Sunday customers. Okay. My Pearson has been... it's usually about a 75 after curve. Yeah, it's a tougher test. It's a tough test. So be studying, be practicing. Statua 1, chapter 14 quiz. Here we go. Let's do it. Yeah, it's a good question. So what's the first thing we should notice in this question? Yeah, it's a tough test. What is the first thing we should notice right here in this question? What is the first thing we should start getting from it? Whenever you get a question like this, it says a grocery store's receipts show that Sunday customers purchased have a skewed distribution with a mean and a standard deviation of. Suppose we had 303 customers this Sunday. So the first thing you should do is you're looking at someone's receipt. What am I about to ask you? If you're doing these questions and you've been, and we'll do standardized test here, I think, coming over soon, you got it, Blake. So if you're looking at these questions and you've been practicing along, so what should you do first? You have a question like this on the test, let's say. First thing you do is what? First thing you do is what? These are the steps. If you're watching this right now, learn these steps to solving problems like this. Don't do anything yet. It does remind you of the way to write this, right? So it's the first thing we do when we get a question like this. We're going to do some notation, and that is correct right there. So let's throw some points. We're going to do notation. So how do we know what notation to do? So this is where usually an error is made. How do we know what notation to do? How do we know what notation to do? Remember, we're looking at a receipt. Quantitative versus categorical. Exactly, Shelby. So we're looking at a receipt, which is how much someone spent. So is this quantitative? Is this categorical, which is going to be the receipt for how much someone spent? So you have to first identify, is it quantitative or is it categorical? And it is quantitative. So make sure you identify, are we dealing with quantitative or categorical? Then go to your formula sheet, and that's the practice key. Go to your formula sheet, and on the formula sheet, select the quantitative distribution modeling notation. So from here on out, you will only focus in on this sort of stuff. So what am I not going to be looking for? What notation am I not? This is a reverse question. What notation am I not looking for, which will not be part of the answers to these questions that we're doing? Q, which is the complement of the true proportion, because that's all categorical stuff. We won't be looking for P, so you don't want to find P, P hat, Q. All those things up there are not what we're going to be using. So we won't use the categorical stuff, which would be like, percent of people who buy an item, percent of people who are in state, percent of people who go to Taco Bell. If it's categorical, like do you go to Taco Bell? Do you own a cat? All those things right there would be chapter 13, not chapter 14, which is the sampling distribution of the sample mean. So now that we know which equations to be using, that's going to be a huge help. So now we need to go through and mark that notations. Let's get to do what we want. Exactly. So now we have to mark the notation. So what should we mark right here? What is something we can mark? Be very careful. If you can mark all the notation, you're good to go. So what is something on here you see? Don't start solving the problem yet. Don't worry what's asking. Mu, which is the mean of the distribution. Exactly. That's going to be 26. Great job. That's mu. That's the true mean is mu. Then what else do we have? We've almost got it all. Number of customers, which is going to be n. There we go. And standard deviation is sigma. I'll draw the sigma. There it is right there. There's the sigma. So we've got everything identified. This is mu. That's sigma. And that's n. And then this right here is it's asking the probability of getting at least this. Now, this is the total. So how can we find out the average a customer spends? So if this is the total, how can we find out the average, which would be an average spent by a customer, which would be a y bar? If that's the total, how could we get an average, which we'll start to look at right here? Divide by the total number of customers to find out the average right there. So we're just going to take right here and do 8100 divide by the 303. It should be like, was it going to be like 270 or something? 303. Good band. Oh, wait, what? No. Spending $26? Really? Someone check that math. Yeah, $26. Yeah, because it's it's a convenience store or something. That makes sense. So there's the sample mean divided by the customers. Yep. I was thinking like real grocery store bills, not like I don't know who wrote this question, but this is a convenience store, probably not a grocery store. I don't know. Maybe a lot of people go in and buy little bits of stuff. Little bits. So we want to estimate the probability of them getting this. So what should we solve for first? If we want to draw the sampling distribution, we should probably solve for the what of the distribution and the what of the distribution. So if we want to solve and we meet the conditions, because it says it's only lightly skewed and we have a huge sample size, so we need to find the what and the what. They put what you need in the back so you buy more exactly, the milk and all that stuff. So we need to solve for the what and the what of this distribution. What do we need to solve for? Nice and pretty. We need to solve for the mean. Oh, not the well, we have the sample mean, and we know the true standard. Well, we know the true standard deviation. We need to find the standard deviation of the sampling distribution. So the mean of the sampling distribution is just the mean, which we already have. Because if one customer spends on average $26, we'd expect 303 customers to spend on average $26. So that would be the mean of the distribution. Now the standard deviation is going to be the original standard deviation divided by the square root of n. So we take the original standard deviation, which was $19, and divide by square root 303. So there we go. I think we use, we're going to use the output one. We're going to use the output here in a second. 303 square root. Let me make sure I didn't click something. 303 square root. 19 should be a little bit bigger than 1.09. So 1.09. You won't use the applet. We would maybe have you find the z-score for this. So now that we know the standard deviation, this value right here is 1.09. Could you find the z-score, the standard deviation of y bar? A very fair test question would ask you to find the z-score of this. And just take a look. If I do observation, I'm now solving this equation right here. If I do observation minus mean over standard deviation, what do you notice about where this is at? It would be somewhere right about here-ish. And what do you notice? So what do you notice about this? This is something you could solve for. That value is going to be about what? And we'll see this when we plot it here in a second. And this is the deeper understanding you want to have. So if you were to take this value of 26.37, 0.73 minus 26 divided by the standard deviation, you get 0.67. 0.67. It's less than one standard deviation away. So it's will the lab 8 video in class for that's for 320, is it, Kyle? 320 or 320? Is it 320? We go over everything in class. Woohoo! Trying to think which class that is for. We'll be doing in-class work on it. And so let's think here. The probability, 4 decimals. Oh my gosh, this is so hard to guess with 4 decimals. It's very close to that right there about. It's very close to that. But let's go to the David M. Lane applet. And on the David M. Lane applet, which we wouldn't use on the test, but you could be asked to find like z-scores for the test. Sorry, 474. Yep, we'll be doing over in 474. Sorry if it says we'll make sure we do them in class. So we will be doing all the labs in class. We do labs in 320 also. So we need to put in the mean and the standard deviation right here. The mean of the curve was 26. The standard deviation of the curve was 1.09. Now I'm actually going to go and solve the standard deviation again to carry all the decimals. 303 square root 19 divided by. So it's that right there. And so we put this in for the standard deviation. There's the curve, and this is what I was drawing out on the bottom of my sheet. Try to draw it out. I didn't carry through the standard deviation, but if I had added a singular standard deviation, I'd get 27.09. Who follows this work right here to understand that I've now added one standard deviation, which this is the new standard deviation for the distribution of the sample mean. But does that make sense how I'm able to do this without the applet? The applet is just going to visualize it for me and find more exact probabilities. We could ask you to find things like the z-score. I understand, but I don't think I can execute it on my own yet. Which part, Shelby? Let me know which part. You want to put in the mean and the standard deviation here in the applet. And the mean and the standard deviation are the original mean of the distribution. Right up there, the original mean was 26. And then the new standard deviation is the original standard deviation divided by the square root of n. The drawing and the calculating, and this is the practice right here. Wait, how would you find the probability on your own? You would know it's probably larger. Here's something you would know for certain. This probability over here on the right has to be more than what percent? So this is a fair way to ask it on the test. This probability right here, if you draw it out, has to be more than what percent? So think, as I draw this right here, it has to be more than what percent? So think about between here is 68. Close, more than 20. It's actually very close to 25, more than 16, because that's the one standard deviation right there, where if you go outside of it, there's 16% on either side. So it has to be more than 16, but less than what? So I'll only show those arrows. It has to be more than 16, but less than what? That area right there has to be more than, exactly, chapter 5 clutch right here. More than 16, but less than what? So the big arrow right there has to be less than that. It's less than, like, if we were to say, carry this arrow across and graph the area, it's less than that. And how much is that arrow worth? So that arrow is right in the middle of the curve. So the area is somewhere between 16 to what percent? This is how we could ask you to solve it theoretically. Great. Yeah, Shelby. Yep. And 50%. So great job, Shelby, knowing that between here and here is half of, that's the same color. We don't want that. Half of 68. That's a really great solve right there. Shelby, that's worth 1,000 points. So you solved it right there using adding the two areas, because between 0 and 1 standard deviation is 34%, but also from the middle over is 50%. So Shelby went and found 34 by cutting 68 in half. Great work right there, Shelby, and good practice. So that is what you want to be able to deduce. I split the 68 in the middle, split the 68, right? And so, or split the 26 between here and here. Best concept ever. It is. Shreya, good to see you here. We're talking about that normal curve, and we use it in even the upper level classes to z-score stuff, to standardize. Normal curve is a huge part of statistics, huge part. And so now we go back to here, and that was my guess, but let's find out the actual answer. So we need to go above where we landed. So we're going to find all the decimals to it. The customers spent, we're going to the Y bar right now, which was 8,100 divided by 303. And it's 26.73. That's the Y bar we found, the observation. And does that look like my graphic I drew? My little quick sketch over here. Do these look similar? Yes or no, and some are good to see you here. Do those look similar? Not exactly the same. That's what we want to practice. Is I knew where it was at because I knew it was between the 0 and the 1 standard deviation. So close enough. And how was my guess? 25. We should have just guessed 25%. I wonder if it would give it to us on the rounding. I guessed 26. If I had just changed that to a 5, it might have given it to me. So we might have gotten it on a guess. But it's 25.1 and it looks like 0. We were very close because I know some additional stuff right there. Now, the last one right here says, if on an average Sunday, the store serves 303 customers, how much does the store take in on its worst 10%? Now, tell me, is the worst 10% on the left or the right side of the curve? We should have just guessed 25%, right? Is the worst on the left? Think you're making money. Is the worst on the left or the right side of the curve? It's going to be on the left side. So copy this number right here and go ahead and put 26 and this. Does everyone see? You're going to go to this one right here, which allows you to put in percent and go to the worst. I think it said 10%. And then we want to do the bottom, and that's the spot. Is it the worst 10%? Let's double check. The worst 10%, and that's over here. You need to put in the percentile to get the bottom 10%, then do the mean at 26, which is what the curve has, then put in your proper standard deviation. And this is the what receipt at a restaurant, or at a restaurant sounds better, grocery store. That is the what receipt of 303 customers on their worst 10% of weekends. That is the what receipt. It's not a receipt. It's the what receipt. Because this is the sampling distribution of the sample mean. Good to see you here, Evan. This is the sampling distribution of the sample mean. So that is the what receipt. That's the average receipt. Does that make sense? That is the average receipt for a customer on it. So that's the average. So what should we do since this is the average receipt of 303 customers? What should we do to find out the worst 10%? Multiply it by the number of people because that's the average receipt for these people. And so we take that value and multiply by 303 and we get the following. So round to 2 decimal places should be fine. But no! Would we have got that if we guessed 26.01? I don't think it would have given it to us. Oh, if I had just put 25 here, would have given it? Oh, you got to be really... These, and do realize, so I give points back if they're super close. You got to be pretty close. So if you're, like, if it's just the last decimal or two, then you're fine. Like, they should give a little leeway on this one. Yeah, you see, this one has more leeway. Oh, you got to be pretty close. Carry those decimals. Especially that last one right here. I'm probably going to be more forgiving on this, especially if you get the first and your last one's a little bit off. They're usually good about how they do the calculations. I'd put a plus or minus 10 on that because no one's going to, like, guess the right answer on that. You have to be really lucky to guess it. Feel free to email me. I'd say 95% of people get their points back. But if you're way off, if your answer was something like 22 on this, ooh, that's no. If you had answered like 25.2, I'd give you the points back. It's 25.1, right? So if you do that, if there's a rounding, or even probably up to like 26, like if you had said, I don't know, if you're like, I guess that, I'd be like, oh, you understand it. Like I would frankly allow you to, like if you had drawn it out and given a good guess on it and said that's about 25%, I'd be like, seems like you understand it well enough. I think we have another question right here, but Shelby, does that make more sense? These are some of the toughest questions on the test. The multiple answers are the best. Scoring 100 is very most. Exactly. And remember, just you have multiple tries, so it's more practice. These are some of the toughest chapters. So we have another one. The other one was a standardized test. Good question there, Blake. A standardized test. Let's put a little chill music on right here. Chill music. A standardized test. A standardized test for step 2. Sometimes I hear these songs on other YouTube videos. So I'll be watching someone's YouTube video and I'll hear this song. I'll be like, hey, that's my song. It's funny because I'm like, that comes from the YouTube library. A standardized test. Ah, we found it. We found it. Okay. Ooh, this is a tough one. Please drop those questions in the chat. I have them. 93 hours is insane. Oh my gosh, you want to see my hours? We looked at my hours just a moment ago. Don't got anything from yesterday. Yep. I also want this one good. It's a good one to practice. So let's take the notes here on which one we're covering. Good practice. And thank you so much, everyone, for being here. So 21, 33, step 201, chapter 14 quiz. Here we go. Let's do it. Evan hit that 1 million. Nice work right there. So what is the first thing you're going to do when you see a question like this? Before doing any solving, before even reading further, what are the steps? So I want you to practice these. I want you to put them on some note cards. I want you to know this. No. I'm sorry, Evan. What's the first thing you're going to do right here? We'll drop some more points. What's the first thing you need to do? Notation, correct?
Notation, brother.
Shelby has it right there. Shelby going to earn some points. We'll drop those points here in a second. We need to determine the variable type. So this says scores on a test. Finish my sentence. Scores on a test are a what variable? You know what? Tell everyone. You come to office hours, you get some 20K points. We'll just be real and nice right here since you missed it. There you go. It's quantitative. Scores on a test are quantitative. Like, how much was your score? Scores on a test are quantitative. We like to throw some fun points right here. Bruh. Some craziness right there, Wes. We have some fun. We have some fun. Point system is getting affected by the inflation year by it does, right? Well, that's very kind of you. So we have right here the equation for the quantitative. Be careful. What will, and I'm repeating this, what will you not have in this notation? What will you not have in this notation? Tell everyone I give big points the week of Thanksgiving where people don't show up. Ah! And then people don't know that material. Ah! We have no P, no Q, no P hat. None of that stuff. None of that. That's all categorical. You say, what's P hat? What's Q hat? What's successes and failures? All that is categorical stuff. So that's where you have to be careful. And you're like, well, wait, I need to check the success. Are there at least 10 successes, 10 failures? No. The condition on this is the large enough N condition right here. So it's election day. What? So who cares?
It doesn't matter.
When you say no pickles and Chick-fil-A, they give you double. Just do that and then get extra pickles and just give them to me. I like the pickles. I'm good with that. A standardized test for graduate school admissions has a mean score of this. What have they just told you? What have they just told you right here? Has a mean score of this. Come get them. Just keep. I'll be there in 7-8 months. Mu. With a standard deviation of sigma. Remember, I can do all these, so practice along. Great job. Shelby, great work. We're going to throw some more points. Keep it up, Shelby, right there. They ruined the bun. Oh, no. That's horrible. Oh, they do. I can see what you're saying right there. So remember, practice this notation. The notation is going to be very important to solving this, as we see with this problem right here. Okay. So with this, we have two classes, a small class and a large class. Now, both of these can be called this. So what is this going to be right here? Both of these are going to be called this. Both of these are going to be called this. They're both N. They're both sample sizes. So I'm going to call this sample size 1 and sample size 2 because we have to do it 2 times. So we have 2 different distributions. We have a distribution for the small class. So the small class is expected to score what on the test? What do you expect the small class to score on the test? So we have small up here and large. What do you expect the small class to score? What would you expect the small class to score? So the test is known to have an average of 147. Evan's doing some great solves right there. Well, be careful though. Guess the score of the small class. Guess their average. Guess what their average will be. What do you expect their mean to be? So if you hear what I'm saying, what do you expect their mean to be? Well, historically, the test has a 147 average. So what would you expect the mean of the small class to be? What would you expect it to be? 147. Does that make sense? Now, it might not be 147, but that's probably the most likely thing. Does that make sense? It's if historically this test, think you've got two classes, and historically this test has 147 average, well, then probably if these students, 9 students take it, they'll probably have a 147 average. Not saying they will, but that's probably the likely thing for them to have. That's the expected sample mean. And that's what that reads right here. It reads expected sample mean. And that is the value right here. Mu y bar is right there. Does that make sense? That is the mean of the sample mean. Exactly. Well, the mean doesn't change as sample size gets larger. Not as the mean, good notes right there, Shelby. The mean does not change for larger sample sizes. Correct. The standard deviation does get smaller. Shelby, another 1,000 points. So I would say the mean does not change for larger sample sizes because it's still just the same formula here. Mu y bar equals that. And so we would get right here, we expect the small class to make a 147. We expect the large class to make a 147. Does that make sense if I say that? Like, this test has a... No, that's all right, Shelby. Don't worry. I can't spell. I can't write. I'm horrible at grammar, so I appreciate you right there. Yeah. Thank you, Shreya, for that positivity. We're here to practice. That's what we do. So I expect the small class to make a 147. I expect the large class to make a 147. But think about this. If you're in a class of 2 people and the person next to you is Shelby, who's acing the class, what's Shelby going to do to the average? Shelby, you're doing a great job. Person's acing the class. What's that person going to do? I'm just throwing some positive vibes. Not talking any grades or anything specific, just throwing positive vibes out there. That person who's acing the class is going to pull up the average. So would there be more variation in a small class where like what the average would be of 2 people or the average of 200 students? Which of those would have more variation? If you took 2 random students and looked at their average, or you took 200 random students and looked at their average, which of those would have more variation in it? So you would take 2 students and average their grades and look at the variation in that. And there'd be more variation with 2 students, right? Because if you get a really high student or really low student, there's going to be more variation for the small group. And you say, well, doesn't larger people have more? No, but you're taking the average of those 200. Does that make sense? Think with 200 students, it'd be super like you'd probably see about 147. Now, it doesn't say 200, but it does a small and large sample size here. So luckily for us, they use perfect squares. So the standard deviation is sigma over square root of n, and Shelby rightfully pointed out that as n gets larger, the standard deviation of the sampling distribution gets smaller. Curve it. Well, it probably will be. I can't say promise, but we often do. I can say we often do. It's expected. If we look at the percent of time, we could use the naive model to make predictions, right, Shreya? So the naive model would predict that we are probably going to curve exam 2, according to the naive model. Throw a little 32474 in here. I love stats terms. Shreya can tell you about the majority level on the naive model. And so now we have a 9 divided by square root of 9. Don't make a math error like Brian did yesterday. 9 divided by square root of 7. I think Evan, or square root of 49 right there, which is 7. So that's 9/7, which is 1.222, and that's 3. So that's 3 and 1.22 repeating. Okay. Large, is that right? Oh, it's 7ths. It's 7ths. Oh my gosh, what is wrong with me? That's 9/7. Thank you, Evan. 5,000 points correcting Brian. Should have put it in the calculator. You got it. That is what we do. You correct me. You get the points because that's why we should use calculators. 9/7 is that right there? Oh, it's 5/7. Darn it. 7ths are interesting because if you look at them mathematically, 1/7, just a quick rant about this. 1/7 actually follows 14/28, and then the 56 is kind of because you get the extra addition, which are multiples of 7. It's 7 times 2, 7 times 4, 7 times, that'd be 7 times 8 right there, right? 7 times 8 is 56. But then it adds that extra, and then it bounces back. So 7ths are very interesting in the way they work. I don't know. I like numbers. I like turtles. So here is the distributions. Once again, we see that the larger class has a smaller variation and the smaller class has more variation. They both have the same expected mean. So let's take a look at the questions. Would you expect the sampling distributions of the mean classes to be, what would you expect the sampling distribution of mean class scores to be, of mean class scores? We'd expect them to be what? A, B, C, or D? Which would we expect? So we have the answer on the other screen. The answer is on the other screen. It's right. That is the answer. So we'd expect them to what? Yeah. So what? So they are 9 over square root of 9, and exactly. That is correct, and we just solved the mathematics. So what answer is it right here? So we have the answer over here on this screen. I've circled the right answer. This is the right answer in this box right now for what the answer is. If we know what this reads, both will be 147. Well, it looks like, so what else will they be? So the answer, one of these is the answer. No. So we can determine it. It's not going to be C. Approximately normal, right? B. No, I was like, thank you, Evan, right there. Approximately normal. I was looking at mine. Yeah, good work. No, good work, Evan. 30 some more points. That's, yeah, no, I was like, no, it's going to be C. It'll be approximately normally distributed with a mean of 147. So here we get to the harder parts of the question. It wants to know about 156 and it wants to know about 142. 156 and 142 are both hypothetical averages, and it wants to know for the small class and the larger class. And it is more likely, it is more likely that the blank will have that success, the smaller class. Okay, so we'll answer those real quick, and then let's find the z-scores of those. Okay, so to find the z-scores, let's look at the values again. It's 156, 142. Okay. 156. Both of those are hypothetical whats. Tell me what I'm highlighting right here. Both of those values are hypothetical whats. Both of these values are hypothetical whats. Bye, Shreya. Great work. Thank you for being here. Both of those values are hypothetical whats. And good to see you, Lauren. Hypothetical means correct. Hypothetical what means? Correct. They are means. Hypothetical what means, though? It's a hypothetical what mean for that class. Y bar means, and what are Y bar means? Hypothetical sample means. So it's to say maybe that small class could have a sample mean of this, like, because they're just a sample of students. So that small class could have a sample mean of this right here. Just love all the positivity in the chat. That's what we're here to support. So now we go in and we solve it out. Okay. So I think the first one was 156. And now we need to divide by, okay. I remove my oh, that's all right. And so now those will be the answers to the first round. And then the second one's 142. That's interesting. Yeah, that's weird. It does that. Some people in class, I think, do. It's whatever people want. So 156 minus 147. Oh, that's easy. What's it on? Yeah. And keep clicking my buttons. And 156 divided by 147 divided by 1.28. Oh, wait, what am I doing? 156 minus 147. What am I finding? What am I currently finding right now? I'm finding all the whats. I'm finding all the whats. I'm finding all my whats right here. I'm finding all my z-scores. Technically, these bottom ones are negative down here. So 1.66. And that's small class and large class. Yeah, that's right. 3.8888888888. Okay, as long as we didn't make a math error. As long as we didn't make a math error. Good to see you here, Alan. 37. There we go. 371663888. Okay, as long as we didn't make a math error. 37166. How many? 2 decimals. 3.89. No math errors. No mashed errors. Woo! Ooh, scary on the math errors right there. Scary. That's the scary. Someone stopped the screen on a really bad moment and then screen share. Oh, thank you so much for all the positivity, like, to each other right there. I appreciate people being don't read. I'm so confused. I'm so confused. We love positivity. That's what we're all about. What other questions should we do? Oh, I'm so confused. Turning red, apparently. What other questions should we do? Good question right there. Pretty laborious. A lot of work. Knowing your notation's key. Know your means, your standard deviation. A researcher measures the waist size. Does it have all the theoretical values? Which one does that have, Evan, afterwards? What does that have afterwards? 37, 38. Compensations of CEOs. Chapter 14 quiz. Compensation CEOs. Okay. Weight size. I think I got it. All right, this is very similar, so this will probably help Shelby out too. We'll do the other one here in a moment. Let's do this. Okay, so with this right here, what do you have to know to start? We're measuring waist size. So Shelby's been getting this right all day. First thing you're going to care about with any question like this is you have to know waist size is a what variable. What do you have to know about waist size? So we're going to know that waist size is a quantitative variable. Waist size is quantitative, So with waist size being quantitative, we know on our formula sheet, so check out the Review 2 page if you haven't. And the Review 2 page has all the review material, also has the formula sheet. Waist size being quantitative is going to use the following to do the distribution of the mean. So what's the first thing you should identify right here, where it says they are measuring the waist size of 242 men. Now be careful, they're trying to trick you right here a little bit. And these men have a waist size of this with a standard deviation of this. And they're kind of cluing you in right here with the idea of true mean. That true mean. Oh, thank you right there, Shelby. I'm sure there's some again. The true mean is cluing you in on what right there? That is what it says, that the true mean is this. Evan knows some notation, brother.
Notation, brother.
The true mean is what? Ah, careful, careful. Good review, good practice. P is only for what? It is mu, good practice. We're going to throw some points for answers right there. We practice. So P is only when what? When's the only time we talk about P? Let's go review again. Anytime we say P, it's because we're dealing with a what variable. And great job, Ali, right there. More points in the chat in 1 second. P is only when the Y variable is categorical, only when we're analyzing categorical variables. So good practice there, everyone. There will be no P, no Q, no P hat in these problems. So these problems right here, the one we're currently doing, will have none of this right here. And that's why we always identify first what we're doing and look at our formula sheet here, that we can identify that this is mu right here. So it's very similar, and that's why we always do the first thing of identifying which variable type is it. So once again, and so here, Evan, I'm throwing you 5,000 points. Evan, you're here practicing a ton, and I love it. How easy is it to look at a problem and be like, okay, where's P? Because now we're going to have another problem. We're going to think the third condition is what if we're thinking P right here. If we're doing, okay, we're looking for P, I'm probably thinking my third condition is what right now? If I'm looking for P, I'm probably thinking I need enough of these for my third condition. Exactly. And you'd be looking for P hat, like what's the sample proportion? And what third condition might we be thinking of? We'd be thinking of I need enough successes and failures, right? But that's not the third condition right here. The third condition is large enough n to see if it's nearly normal. So the third condition, because it's quantitative, is that n is large enough. And that's kind of where they're going with this question with the sample sizes over here. So really great work right there. And just practicing right here and understanding what to use and when. These are different respective sample sizes that we'll be testing there. And then we do have a true standard deviation. So this is also the true standard deviation, which is going to be right there. So what will be the same irregardless of sample size? Irregardless of sample size, what will be the same? Irregardless of sample size, what will be the same? What will be the same no matter the sample size? The mean. Yeah, it's all about that practice. We do problem that user proportion equation. Yeah, we could do one soon here because we need that practice. We need to switch it up, and that'd be chapter 13. And if you know the mean, well, then the mean is just going to be the mean for these. There you go. That's the answer to all of them. Now, the standard deviation, we have to take the original standard deviation right here, and this is the standard deviation of the sampling distributions of the respective sizes. The standard deviation will need to get smaller by a factor of what? Like I need to take that standard deviation right there. If you saw the formula sheet a second ago, so I need to take this standard deviation right here, and it needs to get smaller by a factor, basically n, kind of square root of n. I accidentally did on one of my tests n, I believe, and then that was wrong. But don't worry, 2 square root. So I'm just dividing it by, there we go. This is one of the ones, if you don't round properly on the last digit, I'll give you the points back. That should be rounded properly. We'll find out. 4.043. 3 digits, right? And square root of 10. That's almost pi, 3.14. And square root of 20. There it is right there. What do you notice about the standard deviation as n increases? What do you notice about the standard deviation as n increases? What do you notice about the standard deviation? It gets smaller. Now, if you're off by a tiny bit, I'm fine with that on the standard deviations, but you can't really be off on the means because the mean should be this. These are the simulated values, which the simulation shows what we would expect to see over here, that the means are basically the same and the standard deviations are getting smaller. Our values are kind of close to them. They don't have to be exactly. So don't just copy these values. You can't just do that. You can't say, oh, it should be that value. And also the mean is going to be the mean. That is the formula over here to say what it should theoretically be. And this is what a simulation did. They should also increase their simulation and then they'll basically get the right answers. But then it would show the right answers. So they don't want to do that to make it a problem where you have to solve it. How close are the values? They're very close, reasonably close to. The theoretical standard deviations are reasonably close also. So their values we saw are very close. Looking at the histograms, at what sample size would you be comfortable using the normal to describe the sampling distribution? This is always one of the ones where if you get it wrong, I'd probably give you points back. So looking at this right here. Yeah, I think I said it has a tiny bit of skew right there. So I think it went to 5 yesterday because it's got a little tiny tail right there. So because it's basically normal, The sample size does not need to be very what? This is the something enough condition. So since it's basically normal up here, it gets more normal as n gets thisser, but n does not need to be very this. If you notice here, this is the original parent population. This is means of 2. This is means it can pass. Yeah, I think so with 5, right? That's a large enough n. So 5, since since this is the smallest value, sample size, sample distribution is unimoral and symmetric, which means approximately normal. So all we're saying is it becomes more normal. And actually, let's show this real quick, just so people can see. I want to make sure you understand the concept behind this, because we're not just here to get the questions right. The central limit theorem applet. Oh, whoa. Went to a really random one right there. Here we go. The central limit theorem applet right here. If you have something that is skewed and you do samples of size 2, this is the sampling distribution of the sample mean. Each blue dot is the what of 2 black dots, which is what you're seeing with the distributions we have on the screen. Each blue dot down here is the what of 2 black dots. Is the average, right? So this is what the distribution of the means of sample size 2 would look like. Now, if you go to 25, each blue dot down there is the average of 25 black dots. So there's going to be less variation, but it's still going to be around the same mean. If we do the simulation, look what it starts to approach. How can you have more averages than sample data? So this is like a population of UT students, and I'm asking them, what did you score on the test? And I take 25 random students, and from the 25 random students, I get a blue dot average. We have to clear it out so you can actually see the blue dot fall. But I go to 25 students, ask them what they scored, and then that is the average of 25 students. So it's theoretical, saying what would possibly happen if you sampled 25 random students? What are the likely and unlikely values? And this is a blue distribution for the average of 25 from the original parent population. Does that make sense, Evan? This is probably one of the toughest theoretical chapters because you're going out and talking to UT students, talking to 25 of them, and you're getting one mean right here. And then you're saying, what could theoretically happen? So if you did the simulation a whole bunch of times, like I have to speed up the simulation to show like what could happen. This is the theoretical means you could see. So something over here would be unlikely. Like one student could have this average up here, but for 25 students, it'd be very unlikely to see that. So that's what we're drawing out right here. And we're seeing the distributions. And notice how the standard deviation gets smaller. It goes from 26 to 50, where here it's 33 to 40. Is this distribution thing going to be on these? Yeah, kind of. There's some no written interpretations, but this understanding is very important. To know what you're doing is very important. What about the shape of the distribution of the waist sizes? Explain your choice clearly. The distribution of waist size is unimodal and symmetric. Oh my god. I think it's this one. The distribution of waist size is unimodal and roughly nearly symmetric. Yeah, nearly symmetric. So the sampling distribution of the mean is close to normal even for small sample sizes. That should be right. Woo! When does n need to be larger? You won't have to write interpretations, but when does n need to be larger? N needs to be larger, like 25 or 100 when? When does n need to be larger? When it's more skewed, like heavily skewed, you need an n of 100. Kind of skewed, n of 25. So the more skewed it is, the larger n needs to be. So if you have something that is normal, is too large enough here, such that the new distribution, this is normal, is too large enough down here. If I start doing this simulation, will a sample of size 2 be a normal distribution if the original is normal? So the lower one is just always more normal. And it is correct. Yep. That is also normal because it just normalizes it. So think about the more not normal this is, the larger n needs to be. So if I do a weird custom one right here and make it look all crazy like this, is too large enough now? Will the distribution of sample means of size 2 be large enough for this one, which we have to look at the original shape and say that this is heavily skewed, is too large enough here? No. So now you see it's not normal down here. And probably if we go to 25, it might or might not be. It just depends on if we can draw something skewed enough. See, it's still got a little bit of skew. So maybe we need an even larger, closer to 100, depending on if it's heavily skewed. We like to use the words, but good practice right there. That is the large enough n condition. The more skewed it is, the larger n needs to be. If it's normal, 1. If it's skewed, 25. And if it's heavily skewed, 100. If it's super duper ridiculous skewed, 1,000. But we don't, just the more skewed it is, usually we go 1, 25, 100. Those are the numbers to memorize. Good stuff. Was there another one we've done? A good bit of the questions today. Should we switch over to doing, the CEO ones is very similar. Should we just do the CEO one very quickly? It's very, very similar. Yeah, let's do the CEO one. Shelby, thank you so much for asking. Let's put in, no, let's do it. You asked it. Let's do it. I really appreciate people being here. I always have this fear every semester that it'll be the semester like when no one shows up to office hours. Because every once in a while at the start of semester, people, it's start of semester, so it's pretty chill. And then I'm worried. Now let's do it. No, we're gonna knock it out. You ready? We're gonna do it quick. You ready? We're gonna do it quick. I really appreciate you being here. You guys are so nice to me. So you ready? We're gonna do this one a little bit quicker. The mean for all these distributions should be the what? We're doing this one a little quicker to this is the advanced version now. The mean for all these should be the what? The mean, because this is quantitative CEOs, it should be the same, right? So if we know the mean up there, then it should be 10877.95. Copy, paste. Got it, right? The standard deviation is going to get water as n increases. The standard deviation is going to get water, because there's the original standard deviation. So remember the formula. I'll show you the formula again real quick from the previous page. There's the formula right there. It's going to get smaller by a factor of square root of n, and that's sigma right there, 19 points. So we're going to go 30 square root, 19.4649, and there's that. 2 decimal places. And then 50 square root. And 100 square root, 10. And then move the decimal. I'm going to make an error. Copy paste your best friend. 200 square root, which was an interesting 14, I think it is 14.14. Yeah. I like memorizing stuff. And there we go. How close are the theoretical values? They're reasonably close, and they're reasonably close. Is that it? Oh, whoa. Where did we go wrong? Where did we go wrong? That's why I'm going to do something too quickly. No, that one's right. Decimals, where's my 5,000 points. Brian getting a question wrong. People, I should have read the chat more. I was going speed run on the question. If you had gotten that wrong, you could email me. I was zooming. Yeah. I was like, where'd I get something wrong? Where'd I put that wrong answer? If you got that wrong because you put an extra decimal, please email me. There we go. We did everything right. And my Pearson's like, you're too exact. Yeah, does that make sense, Shelby, right here? Really good. Another good practice, knowing how the standard deviation gets smaller as the sample size increases, and the simulations show reality. So these values are going to be very close, and it's very similar. Gave you a 90 for that, exactly. Points for wrong answers, exactly. Thank you for everyone being like, whoa. Good check. You know to check your decimals. I really wish I don't know. Let's make my life easier if you just counted it. Be like, hey, you put an extra decimal. That's all right. Just being more exact. So let's do one on the sampling distribution of the sample proportion. So remember, I was watching the train. Sadly, no. Let's do the sampling distribution of the sample proportion right here. So remember, this is going to have completely different formulas. I mean, they're similar, but they're a little bit different. So make sure to do this right here. And great work. I hope people have those hundreds on these. These are tougher quizzes. These are not the easiest. I've not created any assignments. Apparently, I've created no assignments for you. Assignment manager. I think it was announcements I did by accident. Got it. No assignments. What? Cool. Like Brian says, he's doing no assignments. Okay. So, chapter 13 quiz. Pick a number 1 through 12. Pick a number 1 through 12. Pick a number 1 through 12. Evan. 7. As the sample size increases, the mean of the sampling distribution does what? Here, we'll do this. We'll call this review. What does the mean do? So this is 56, 13, Stat 201, Chapter 13, Reviewing Quiz. Stays the same. Don't. I'm kidding. Let me 30,000 more. I'm kidding. I think the biggest thing is people realize if I make a joke, then I think you're awesome. So, exactly. If I make a joke, it's because I'd only make a joke with people who I think are, that I'm that are having a good time and enjoying and having some fun with. So, thank you so much, Evan. Right there, some points right there. Cracking us up in the chat. So the mean stays the same no matter which one we're talking about. Right here, no Game of Thrones, no shame. Ding ding, shame. Bing bing. Yeah, no, are you talking about like people like Shrey and everyone? It's weird that there are involved students who involved, like, yeah. I haven't check out some Game of Thrones. I was really into that kind of stuff. Game of Thrones is awesome. Say the same. Pick another number. Yeah, no, we get everyone involved here. Can we do another CEO question after this? It has graphs that have the skew. Yeah, Ali, let's do it here. We'll do a little more of this, then we'll do the other CEO question. Star Wars greater than Game of Thrones. What number should we do now? And then we'll do the other CEO question. Pick a number. It could be up to 12. First number in the chat. I've been top chat this whole time. Pick a number 1 through 12. Doesn't even. Parfait. Merci beaucoup. 3. Let's go 3, and then we'll do Ali's question. All right. Here we go. The proportion of adult women in the U.S. is approximately 51%. So this is someone a woman or are they not a woman? So what is this in notation? What is this in notation? This is a what variable? This is a what variable? What variable is this? Oh, sorry, no. It's categorical, so it's P. Because the proportion of women, if this is true, makes that P. And as soon as you find P, what do you find immediately then? As soon as you find P, what do you immediately find? If I know P is equal to 0.51, that's women, proportion women, I'm going to find what immediately? Like if I'm like, okay, I found P, which is the true proportion of women, because it's like the proportion of women in the United States is 51%, I'm going to instantaneously find what now? Not biased, good. I try not to be biased. What should we find now? If you find the true proportion of women, you should find the what instantaneously notation-wise. Q. Yep. Now we find Q. How do you find Q? Don't worry. A lot of people say, and then we could find N, right? Which is sample size. A lot of people say to me, well, how do you find Q, Brian? How did we find Q right there? How did we find Q? Remind everyone of the mathematics to find Q. To find Q, it's simply 1 minus P. And 1 minus Q is P, 1 minus P is Q. They're simply complements of each other. So now that we know this right here, it asks us in the first question, what is the mean for the sampling distribution? It says, like, what is the expected value? What is the mean? So knowing the notation right here, what proportion of the sample of 500 would you expect to be women? And that's literally what this reads. It reads expected sample proportion. So what proportion would you expect of 500 people to be women? What proportion would you expect of 500 to be women? What proportion would you expect? $51, exactly. Yep, that's the proportion. Yeah, that's the proportion. Remember, it is as a decimal. Great job, Ali, right there. Yep, because that's it's just asking right here. It says, well, what's the mean? So there we go. Now it wants us to do the standard deviation. Now the standard deviation we actually have to solve in the formula. So we need to do P times Q over N square root. P times Q over N square root. Quote 191 right there. P times Q over N square root. And so we go right here and we go P times Q over N square root. There go 3 decimals. There it is. How many women would you expect to find in that sample? So how many women would you expect? What should you do mathematically if you sample 500 individuals where 51% are expected to be women? What would you do here mathematically to say I'd expect about this many women? So now it's asking how many, like numerically, we would expect, not proportion expected, but how many expected women would there be? And this kind of relates to a condition. So how would you solve this mathematically? Because you're going to sample 500 people where you expect 51% to be women. So how many women do you expect? You're sampling 500 where 51% are expected to be women. So out of the 500, you expect 51% to be women. So what should we do mathematically to solve this? I think that's right. Just times this right here. And there it is. And you actually just checked half of the what condition right there. You actually just checked by doing NP right there, or PN. You just checked half of the what condition, because that's how many successes there are. You checked half of the success failure condition. So that's the expected amount of successes. Like, not saying you will see that, but if you say, oh, if I sample 500 people, I'd expect there to be about 255 women. So that's at least 10 successes. And then the failures would be 245. You could also subtract from 500 to get that, or multiply the numbers here and get 245. But successes and failures equal up to the total sample size, because you'd expect there to be 255 women and expect there to not be 200 people you expect 245 people to not be women. All the rules have been to plus this. Sarah says, oh yeah, it's the notation. It's the notation. I've been teaching these chapters for a long time, and I see when people get to the test and they look at this question, they say, I don't even know where to start. They say, I look at it and I'm like, I don't even know what it's asking. What proportion of sample would you expect to be women? Well, that's just the formula. It's saying expected proportion right here in your sample. That's what that reads. Expected proportion in your sample is the true proportion. So if 51% of people are women, then if I sample, I'd expect to see 51%. The expected in my sample proportion. I expect in a sample proportion. The standard deviation of what we'd see in a sample proportion is this. So when you read this as expected sample proportion, it makes a lot more sense to say, if I were to take a sample, I'd expect to see this sample proportion. I'd expect to see the truth. Now, the variation is going to be based on sample size, which is going to be smaller variation at larger sample sizes, and vice versa, larger variation at smaller sample sizes. Let's do the other CEO question to end off right here. Thank you, Ali. So really good practice. It's all about that notation. Remember, write down your notation and know it. So the other CEO question, right? Let's go grab that. Other CEO. You bet. How does it reads what again? I think I know where it's gonna be at. We've got about less than 10 minutes. The histogram to the right shows the got it. Oh, let's check it out. Taking the note for it. 104. Scram to the right. Let's check it out. It's more the last question I'm confused about. Oh, cool. Let's do it. Here we go. Okay, the histogram to the right. So this is a bit of an interesting one. It's a bit of a weird one. It's kind of one of those, like, it doesn't always work cases. So there's the histogram of the data, and it's very, very what? How's that monster man looking today? Now, this is compensation rates, which is quantitative. Skewed to the right, right to the high, left to the low. Whatever way the Monster Man's tail goes. Right to the high, left to the low, whatever way the Monster Man's tail goes. So it is definitely right skew right there. So we've confirmed that answer. Explain how these histograms in the simulation demonstrate what the central limit theorem says about the sampling distribution for the sample means. Okay, so the central limit theorem states two things. One, the distribution will become more what? One, the distribution will become more what? The distribution will become more what? It'll become more normal. So here's the original, more normal. You see sample size is increasing. More normal, more normal, more normal, more normal. Two, look at how it goes from 0 to 24,000, 0 to 24,000, and here it's going from like 0 to 17,000. Also, as n increases, what else happens? As n increases, ooh, my Pearson, you being a little weird. I need to fix. That's an error. The standard deviation gets smaller. Don't look at that. Look at what they show in the simulation. Notice here at the larger sample size that the graph only goes starting here at about, that's 4, that's 2,000 bin to 18,000, where in the top bins it goes from 2,000 to 22,000. So it has smaller standard deviation, less variability, lower standard deviation. So the peak of the histogram is around 6,000. Notice the peak. What is happening to the peak of the histogram, which started here at about 6,000 and over here? School, work. What is happening to the peak of the histogram? The peak of the histogram, which is at 6,000, is doing what? The peak of the histogram that's at 6,000, it remains the same. And then take a look at our equation. Do you see right here that the peak of the histogram is where the mean is at? Because mathematically, the mean doesn't change. Does that make sense? The standard deviation gets smaller, the histogram gets more normal, so it gets more normal as n increases, it gets less variability as n increases, smaller standard deviation. The peak stays about the same spot. Great answer right there. So that peak right there is about at 6,000, because that's 4,000, that's 6,000. There's where the peak, 6,000. That's 4,000, that's 6,000. It's about the peak. 4,000, 6,000, that's where the peak is at. 4,000, 6,000, and that's where the peak is kind of at in that. It's a little more right skewed, so it's got peak over there. So the simulations support what the central limit theorem says for the sampling distribution models for the sample mean. As the sample size increases, the peak of the histogram stays about the same. The shape of the distribution becomes more normal and the variability decreases, smaller standard deviation. So if someone said to you 30 is always large enough, is that true? Just don't even look at their responses. If someone said 30 is always large enough, is that true? If someone said 30 is always, don't look at their responses. If someone said 30, no, it's not. Because the more skewed it is, the wider n needs to be. The more skewed it is, the wider n needs to be. 30 is not always large enough. Like 25 is good for skew. 100 we need for really skewed. That's the large enough n condition. So that's what this question's highlighting right here. So since the distribution of means, since the distribution of means for the sample distribution of any size remains skewed, the rule of thumb does not hold for highly skewed distributions. I think that's correct. Woo! Only one decimal error today. So if it's highly skewed, you really need a larger sample size. Since the distribution of means for the simulated samples becomes less skewed as sample size. No, so what they're saying, right? And good asking, yeah. So it does not hold because what they're saying is, with a sample size of at least 30, the sampling distribution will be normal. So the sampling distribution of the mean is normal. So it does become more normal, but it's not normal at 30. If you look at 30 right here, this is not normal. It's still skewed because sometimes we need a much larger sample. So sometimes we need a much larger sample because when it's more skewed, we need a larger sample. So the rule of thumb, like 30 is always good enough. I wish they described it that way. Like as long as you have 30, the distribution will be normal. That's not true. Sometimes you need a much larger sample. Yeah, it's kind of a weird way of phrasing it. Like if I were to phrase that question, I would say like, if someone told you 30 is always large enough to have a normal distribution, what would your response be? And the response would be, if the original distribution, because maybe you look at the shape of it, is heavily skewed, you sometimes need sample sizes that are very large, i.e. heavily skewed about 100. So maybe it's kind of normal-ish at 100. Like I said, super duper skewed, you might need something really larger. Nice job. Yeah. Good to see you, Amanda. Let's throw 1,000 points. We love people swinging by, say hey. And we're going to finish off right here. Nice job, Shelby. Tough quiz and good practice. Super duper skewed. So with that, we're going to head off. We're going to get ready for class. I'll be sending out the announcement. Thank you, everyone. I missed one just because I clicked on the wrong fish thing. Which fish thing? If it's, let me know. Am I corrected? Let me know. I don't correct everything. If it's something like, thank you so much. I appreciate that. Of course, we're doing office hours tomorrow, unless I don't know. We should be doing it. What classes are you teaching next? 474. 474. Let me check your Discord messages. With that, I'm gonna check some Discord messages. I'll be back later. Bye, buddy. Bye.